Hi everybody, my name is Sean McAllister. I'm glad you could join me today. We're going to talk about considerations for scaling your connected vehicle platform. And what I'd like to do today is to bring together an amalgamation of our experiences dealing with customers such as Land Transfer Authority in Singapore, where today we connect over 5,000 buses to their connected vehicle platform. And as that platform grows, we'll be adding over 1.2 million cars that will be connected to that same platform over the next few years, as well as experiences that we've had at Reliance doing massive scale IoT connectivity projects, and then as well at Daimler, where we support their connected vehicle platform, where they add millions of vehicles every year to this platform. And now, in the early days of connected vehicle, people generally went down the path of reusing technology that was well established and that they had, which primarily meant an HTTP-style infrastructure, because web servers, firewalls, load balancers, these are technologies that people knew very well, know how to scale very well because of the modern internet. And it really did allow vehicles to then be able to push data up into the connected vehicle platform itself, simply by issuing a post. And HTTP is very prominent in various architectures, very easily accessible. And so you could upload data, telemetry data about the vehicle very, very easily. And the challenge became more as we evolved to wanting a command and control type activity with the vehicle where you want to interact with it. So for example, in Canada, where I'm based, it's really nice from your office in the wintertime to be able to start your vehicle and warm it up before you get down there. Or if you're rushing to catch a plane and you're not sure if you've locked the doors or not, then after you pass through security, you can use your mobile app to lock the doors. Or in my case, I come back from a trip and I'm wondering where I parked the car, and I want to be able to use my mobile device to honk the horn to see where, to try to find it in the parking garage. So I pull up my mobile app and I get it to honk the horn. And as I was saying, in the early days of these types of connected vehicle platforms where people were using HTTP is not good to be able to reach out to the device. Devices can upload data, but applications can't send to these devices using HTTP. So what many vendors did is they used SMS to be able to send a wake-up message to the vehicle, and therefore the application wanting to honk the horn would send an SMS saying, hey, wake up. The vehicle might do something like do an HTTP GET and say, yes, what do you want me to do? The application would say, I want you to honk the horn. So the vehicle would honk its horn and would issue a response saying, I'm doing that now, I'm honking the horn. And the application would then return something to my mobile app saying, I'm done. Or in my particular case, it might be saying, if you can't hear the car honking, then you're not all that close to the vehicle. And so this worked well in the early days and it got people going. You could do some level of bidirectionality, but the issues with this infrastructure really very much being that the latency, for one thing, was quite high. You look at the number of interactions here, the number of infrastructures, SMS itself is very unpredictable latency. And so if you're near your car and you press a button to either lock the doors or to honk the horn, you want it to be a quick response to your action. And that was very difficult to achieve with this kind of an infrastructure. As you can see from all of the arrows and the interactions, it's quite a complex interaction. The more moving pieces you have, the less reliable things tend to be. It was expensive and really not very flexible, because even though you may bury all the SMS behaviors and everything down in the connectivity tier, it's a very difficult way to be able to send a single command, which is just honk your horn. And you look at all the things that you need to do to make that happen. And so while this maybe got some platforms up and running quickly, really people wanted to move to the next phase and to improve on what they already had. And if you look at what you would like to achieve or what you would like to have in your next generation connectivity platform, you want something that first of all is low latency. Because if you're going to interact with your vehicle, by the time you issue a command, you want it to take effect fairly quickly. You want bidirectional communication, so data uploaded from the vehicle, but as well as commands being sent to the vehicle, Bandwidth efficiency is important to manage costs. Of course, it has to be secure. You would like it to be, and very much require it to be, open and standards-based so that the engineers working on the vehicle could choose technology that is completely independent from the engineers building the platform in the data center. And of course, it has to be scalable to millions, if not tens of millions of devices that you need to connect. What many people did then to move forward is to look at a technology called MQTT. And I have been fortunate enough to be on the MQTT standardization committee for both version 3.1.1 and 5.0. And I'm very happy to see the uptake now in various areas of Internet of Things. And really, MQTT was very much designed from the very beginning to be able to offer low latency, to offer bidirectional communication, to provide bandwidth efficiency, security. It's of course open because it's a standard. And so these are all great things, but from the point of view of it being scalable, that's an architectural issue. That is not something that MQTT can do on its own. So the question is, how do you make your MQTT connectivity tier very highly scalable? And that's what we're going to talk about today. So if you start off, we'll do some basics here, but you put an MQTT broker into your connectivity tier, and you connect your various vehicles to that broker. And MQTT is a protocol that rides on top of TCP, or really TLS is what you would have here. And so with one connection, both the vehicles can send data up to your platform, and the platform can send data down to the vehicle over this single connection. And so as a result of that, now your vehicle that is connected can send telemetry data up to the MQTT broker that it is connected to, and the MQTT broker can then direct that message to one or more applications in your application tier for any of those applications that are connected to the broker. And similarly now, if I want to tell my car to honk its horn, then my mobile app, as before, sends a message to the application tier. The application that sends the command to honk the horn, it is connected to the MQTT broker, so it sends a single command down to the broker and tells the broker to honk the horn on Sean's car. And then the broker knows which of the many, many connections is to Sean's car, so it sends that command to my car honks its horn, and on that same connection that I received the command, the car can then return a notification to the broker that it is honking the horn. The broker can send that to the application tier, and then the application tier can tell my phone that this is in fact happening. And you can see now, compared to the previous interactions, this is so much simpler. It is very much send a command to the MQTT broker and tell it which car that you want this message sent to. The broker sends it to the car, and the car can reply on the same connection. And so that's great. We've achieved many of the objectives that we started out to achieve. But now, of course, even though a single MQTT broker may be able to handle hundreds of thousands of connections, you want to put millions in your platform. So how do you scale that? That becomes the next question. The first thing that you do, the obvious thing, is you deploy more MQTT brokers, as I've done here, and you have your vehicles connect to these multiple brokers. The challenge becomes, as you want to send a command to one of these vehicles, how does your application know which of the brokers your vehicle is connected to? So what could happen is that when my mobile application sends a command into the application tier could, of course, send it to all the brokers and have it discarded on all brokers that my car is not connected to, with one of the brokers sending it to my car and then the response coming back. But of course, this isn't a realistic situation, right? Because you would not want to require all of your applications to connect to all of the brokers and to send so many messages and have so many of the messages discarded. But it was just meant to illustrate the difficulty in having applications talk to a particular vehicle or to a set of vehicles. So how do you solve that problem? And as in many cases with software, you say, well, we should just cluster them together. But not all clustering solutions are created equal, and it turns out it's not always that simple. So what I'm going to do is walk through different forms of clustering with different levels of sophistication to arrive at the solution that we have found through experience provides the best scalability and the best robustness at scale. And we'll go through clustering with flooding, clustering with dynamic routing, and then the third one, which is the optimized topology with intelligent dynamic routing. Now in the first case with flooding, the way that you would do this is you would first of all connect all of your MQTT brokers in your connectivity tier, so now they are a cluster. And that means that your applications in the application tier can connect to one of the brokers in the cluster. And when I want to honk the horn, the application sends one message to one of the MQTT brokers. And now because I'm doing flooding, which means that the brokers are not very intelligent, the broker is the one that would send the message to all of the other brokers in the cluster, which would cause, in this case, broker 2 to discard the message. Broker 3, which is where my vehicle is connected, would send it to my vehicle. The response, my vehicle honks its horn, and then the response comes back. But again, broker 3 doesn't really know exactly where to send the message. So he will send it to broker 2, who will discard the response. He will also send it to broker 1, who will then return it to the application. Now this is better to some degree in that the application only needed to connect to one of the brokers in the connectivity tier, and therefore the number of brokers in the connectivity tier and the complexity of that interaction is all shielded or is all hidden from the application. That's a good thing, but it's still a fairly naive approach that is quite wasteful in terms of the amount of data that needs to be propagated, and so the question is, can we do better? So then you move to option 2, which is where we add some intelligence into the cluster with dynamic routing. And with dynamic routing, what that means is that the brokers in the cluster that are all connected to each other share information in real time about which vehicles are connected to which brokers. And that allows much more intelligent routing decisions to be made. Let's walk through that. So in this case, again, the application tier connects to only one of the brokers in the connectivity tier. And the honk my horn message goes to that one broker, to broker 1. Now, because in this case, all of the brokers share information about which vehicle is connected to which broker, broker 1 knows that my vehicle is connected to broker 3, so he only sends one message to broker 3. Broker 3 sends it to my vehicle, the horn honks, and when the response is returned, broker 3 knows that the response is to go only to broker 1. So that message goes straight to broker 1 and then out to the application. And now what I've achieved is, from an application point of view, I connect to one place into the cluster, and the cluster is quite intelligent and efficient in how it routes its messages. So that sounds perfect. We're done, right? How much better can you be? The problem with this is that in this case, the architecture is such that the complete state about all of the connected devices, which is a large amount of state, needs to be shared with each and every node in the cluster, and that needs to be done in real time, which means that as devices connect and disconnect and subscribe to different types of information, that state about where my vehicle is and the type of information that it wants needs to be propagated to all of the brokers. Also in this case, we have a full mesh connectivity between all the brokers, and effectively there's no hierarchy and no isolation. It's a completely flat topology. Now, why does this matter? Why is this an issue? Well, if I walk you through how we would scale such a platform, and we start off with broker 1, which has its own state for perhaps 100, 200,000 vehicles. And then I add 3 more brokers to the architecture, which means that now I have to add 3 more links to MQTT1, who connects to all 3 of them, but also MQTT1 needs to have the state in real time of the other 3 brokers. And similarly, each of the other 3 brokers that I've added have to have the state about all of the other brokers in this cluster. And if I add 3 more brokers, that is more connectivity and more state that needs to be stored and flooded in real time. And if I just go to even 10 brokers, that means lots of connectivity. It means lots of information being shared in real time. And what do I mean about lots of information? Well, if you look at broker 10 and you have activity there among its 1 or 200,000 vehicles, then as that state changes, it ripples through all of the other brokers in the cluster. And that means that broker 10 floods this information to all of the other brokers who need to store it and adapt to it. And this visual representation is really only broker 10 making changes. This is going to be happening at the same time on all of the brokers as vehicles connect or disconnect or change what they're interested in, which happens a lot if you have millions of vehicles connected. And what can end up happening then is that your cluster is really only as strong as the weakest member. And that means, as an example, that as things change on broker 10, maybe broker 5 is at a point where it's in a state where a certain amount more activity causes it to crash or causes it to misbehave. And so that information from 10 gets flooded to 5. 5 perhaps crashes, and more state information is flooded, and that causes number 4 to crash. And you could see a bit of a ripple effect happening here. And this is all because all brokers need to know everything in real time. And that's just fundamentally a problem, right? If you think about how organizations are built to scale, how the internet was built to scale, it did not require that all members know everything in real time. And this is why, while a full mesh and dynamic routing provides intelligent routing, from a scalability point of view, adding more and more and more brokers creates more and more and more demands on all of the other brokers, which then leads to huge fragility. So you could imagine if I had 100 brokers here, how can you tell as I add broker 100 what the impact will be on all 99 other brokers in the cluster? So in our case, what we did is we said, okay, so how do we deal with this situation? What's the solution? What are the best next steps? So the first thing we said is let's look for patterns in the data flow, because this is a highly specialized environment. Maybe that will guide us. In the previous architecture, we have full mesh connectivity, but do all brokers really need to be connected to each other? Because if you look at the traffic patterns, they really are such that traffic flows from device to the platform applications and from platform applications back down to the device. So the data flows north-south, not east-west. And therefore, you wonder if a full mesh connectivity is actually a good thing. The other thing is the observation that scale drives specialization, and which begs the question of, are there specialized functions in this architecture? Because there certainly is a huge amount of scale. And you observe that there are really, in terms of functions, there's connectivity to devices and connectivity to applications. And these can be different things, and you could treat them differently. And so the question is, if you optimized for those two functions, what could you achieve? Then, because some of these problems have sometimes been solved in other situations, we looked for inspiration from other systems who had perhaps developed techniques that solve these types of scalability problems very successfully. And if you look at networks, networks are classic examples of that. The internet has scaled massively. And if you look at even data centers, for example, where you have many, many servers in a rack, and those servers connect to a top-of-rack switch, and top-of-rack switches do not connect to each other, they connect to a hub switch. So it's very structured in its approach, and that has allowed data centers to have massive scalability of huge numbers of servers. And the other thing is that we really wanted to develop an architecture, very critically, that isolates the impact of growth. And by that I mean, as the system scales and as you add more devices and as you add more MQTT brokers, this cannot affect all of the other brokers in the system. It has to perform an impact on a much smaller, well-defined portion of the architecture to ensure that adding or scaling the platform didn't result in an impact to every member of the platform. Now, with that in mind, if you think about the observation of north-south traffic patterns and the network example that I described, if you thought, hey, maybe this sounds like a tree topology would be much better than full mesh, then you will have come to the same conclusion that we came to. And so what we observed, and the architecture that we have come up with, that we find scales very well, is to have a root node that connects to the application tier, and then to have leaf nodes that connect to the devices. And as you add more devices, you then add more leaf nodes. And every time you add a leaf node, that leaf node connects only to the root node, first of all. It does not connect to other leaf nodes. And so that's step number one, is that you don't provide a full mesh. Because the traffic is north-south, you have a root and leaf topology, which means that as I add broker 100, it connects to exactly one place, the root node, not to 99 other places, first of all. The second thing has to do with this intelligent dynamic routing. As I add more and more leaf nodes, because of the fact that in this case I add leaf node 7, the devices on leaf node 7 don't interact with leaf node 1. And so leaf node 1 does not need to have the state information from leaf node 7. And this is the intelligent dynamic routing, is that as you add more leaves, the leaf nodes need to tell the root node which devices are connected to it. But each leaf node doesn't need to know anything about the connectivity of the other leaf nodes, because as messages come in from the vehicles, those messages are pushed up to the root node, and the root node knows where to route these messages, which is typically up to the application tier, but could be back down to a leaf node if you wanted it to be. So the key thing about this architecture is that as you add leaf nodes, no matter how many, even the 100th, you create one connection to the root node, and the state from the leaf node goes to the root node, which means, back to my premise of wanting a contained way or a very specific place in the architecture that was impacted by growth, it is the root node. And so yes, you very much have to look at the scalability of that root node, but that is really the main place that you have to be worried about or concerned about from a scalability point of view. So now you can have specialization where the leaf nodes have connections that are very wide, right, like hundreds of thousands of connections, but each connection has a very small amount of traffic. So wide and shallow, whereas the root node has a much smaller number of connections, but much more traffic on each connection, so narrow and deep. And the root node can also support all kinds of capabilities that foster application connectivity, like JMS, like Kerberos authentication, all of these things, whereas the leaf nodes support functions that are required by devices. The other thing is that you can now have specialized infrastructure where the root node, if you're in the cloud, could be housed on specialized EC2 infrastructure for its functions versus the leaf nodes, which could be housed on different compute engines. Or in the Solace case, since we offer both hardware and software versions of our product, it's not uncommon to see the root node be our hardware appliance, which is massive performance, and the leaf nodes being our software versions because they can scale to a very large number of connections. And now, as for example, leaf node 7 has connections that flap and come and go and subscriptions that churn, that particular leaf node 7 is impacted, as is the root, but none of the other leaf nodes are affected. So if you had 100 leaf nodes, none of them would even know that there's all kinds of churn happening on leaf node 7. So in conclusion, we've walked through various ways of scaling your connected vehicle platform with various forms of clustering, such as clustering with flooding, which provides for a lot of wasted information flow, clustering with dynamic routing, which looks great at first blush, but then as you find that the control plane can become completely unstable under scale. What we have found is that an optimized topology based on a tree topology, actually, with intelligent dynamic routing, this is what we have found to provide the best scalability and the best robustness at scale. This is what clients of ours, such as Daimler, are using to grow their platform at millions of vehicles per year, and both at a massive scale and with great stability. So thank you all for listening to this. Good luck with your connected vehicle platforms. If there's anything that we can do to help out, please feel free to reach out to Solace. We'd love to talk to you about it. Thank you.